So as Paul mentioned, my name is Praba Santhanakrishnan. I'm a data scientist here at Microsoft. I've been working with Microsoft for almost 2 decades now, working on building various data platforms, large-scale big data solutions. And now for last 7-8 years, I've been spending my time on doing science experiments in terms of how to improve Microsoft products and features, especially in Windows operating system, using data and building scientific experiments using machine learning. And deep learning is the today's topic, so we will be covering some basics on what deep learning is and how it is different from machine learning. And also, we'll get an opportunity to see the demo on how the Microsoft Azure cloud platform supports the training, the deployment of deep learning principles. And part of that Azure Machine Learning, so we have a new services called Azure Machine Learning Services, and also there is a user interface that is available called Azure Machine Learning Studio. And some of them are in preview state, and we'll get to see that. And it is available for you if you go to the Azure portal, and I'll share with you some notebooks that are already available in the GitHub, and it is open source, and you can feel free to start using that for your learning based on what we will go through today. So before we get into the details, wanted to understand what is deep learning. It is a subfield of machine learning. It's a biggest buzzword today in the field of data science and machine learning. When you look at how the deep learning principle differs from classical machine learning, they are applied for different purposes, especially in the artificial intelligence world. When you want to, for example, predict a stock price or predict the weather, you would pretty much use your classical machine learning applications and principles and the algorithms to do that. But when you are pretty much looking at replacing or automating the human intelligence by artificial intelligence, and that's where pretty much deep learning principles are used. For example, if you want to recognize a cat or a dog from a picture, from an image, and you would want to use deep learning techniques. And for example, in the self-driving cars, and if they want to recognize the stop sign or a red light, those are like intelligence that is very commonly you develop when you're growing up, but how an algorithm can figure it out is what the principles and deep learning is being used for that. So it's a subfield of machine learning, but again, it's more than a machine learning. But the key idea is that you learn from the data, the historical data, the intelligence, the insights that you gain, so that you can use that model to predict for any new unseen scenario. It is based on artificial neural networks. For any technology advancements, like we go back and look at the nature and learn from the nature to build any advanced technologies. For example, like basic how the bird flies, and based on that, we came up with the idea of aeroplanes, or looking at the burdock plants, that we came up with the idea of Velcro. Similarly, the deep learning principles also heavily relies on how the nature works, especially within our brains. So we all have like millions and millions of neurons, and that's what will help us to learn anything that we see around, or anything that being taught, which is memory management within your brain, or even perceiving things around you is what is being used in your brain. And the same principle is what is applicable in deep learning. So we have something called artificial neurons, and that's what is known as the perceptron in the deep learning field. And you stack them, several of them together, then you get the deep neural networks. And we'll get into some details on how it is being used. And you can apply this for all sorts of learning: supervised, semi-supervised, unsupervised. You may have heard about these types of learning in your classical traditional machine learning concepts. Supervised is where you know your labels, what you are trying to predict or classify. And in the other extreme case of unsupervised, where you do not have the label data and you are trying to do some clustering techniques to understand what type of data that you have and what type of groups that you can create out of that, so that you can have a better understanding of the data and the classification or the prediction that you can do. And semi-supervised stands in between these two, where you have some labeled data and largely unlabeled data. So you learn from the partial labeled data that you have and you use that for your unlabeled data, right? For example, like classifying music files, and that's the classic example for the semi-supervised. So you can do all sorts of this techniques, learning techniques using deep learning, right? And why deep learning, right? So why can't we just use the classical machine learning techniques that we have? There are some attempts made, but why do we need specifically these kind of deep neural networks? And it comes with a lot of expands and it's very difficult to train, but why do we need it? The key thing is that scale drives performance. It has been proven multiple times that the larger the data that you have, the performance, the accuracy, the F1 score, the recall, in all those metrics that you use to evaluate the performance of your model that you train is definitely a lot better when you have access to the large amount of data. So that's what you see on the graph there. Over a period of time, when you keep adding more data, the performance of the traditional machine learning algorithm kind of saturates. And that's when you see the difference in terms of how deep learning algorithms can give you a much more better accuracy when you have a large amount of data. So that's the primary driver for these deep learning algorithms. And of course, when you are talking about large amount of data, you need access to the big data and the ability to store the data and analyze and process this data. So nowadays, with the invention of the cloud capabilities, that you can get these access to the data and the storage in a much economical, cheaper cost nowadays. Especially every day passes by, these costs are going down, and with the huge competition between Microsoft, Amazon, and Google and other few cloud players, the elasticity is available for you to be able to handle this large amount of data and process them in a most efficient way. And there are some modern hardware being developed while we speak. For example, that you may have heard about chipsets called tensor processing unit from Google. It's the TPU, and Microsoft has something called the FPGA, field programmable gate array. It's more than the GPUs. Like when the CPUs cannot handle the large amount of data, then we switch to GPUs, which are much more powerful. But even beyond that, now we are seeing some specific application specific chipsets like TPU and FPGA. So there is an support that we get from hardware that allow us to do deep learning. And there are some algorithmic innovations also happening on almost again on a daily basis, right? So if you learned a new algorithm, and pretty much 6 months down the line, there will be better than that is, you can see from the community all around the world. And there are a lot of innovation that is happening in this field. For example, like to identify a cat image, about like 3-4 years ago, it used to take several days to run these algorithms and figure out what kind of image we have. But nowadays, those can be done in hours, and if not in a few minutes. And we also have advanced framework support that we get from to do deep learning exercises, right? TensorFlow is one, and PyTorch is another one. So we'll get into some of those details as well. So there's no better time to do deep learning exercises, because you get support from multiple different factors in terms of how you can run this large scale experiments. So quickly, let's go through the concept of the neuron that introduced. So you have inputs coming in, x1, x2, x3. It's very similar to the features that you would have in your traditional machine learning. And what you do in this case, when you look at a neuron, that you combine this input into some sort of addition summation, where you have this different input with the different weights. So x1 has the weight as the w1 and w2, w3, and you add them, and there is an activation function that sits on top of this, the output that is generated by this summation, and the activation function either fires or doesn't fire. So that's how the neuron also work in our brains, and the same principle is that's what being used here in terms of how the artificial neuron works. So if you stack them in multiple stacks, like you have like layers after layers after layer, then what you generate is the neural network. It's a densely connected neural network, right? So this is how a simple connected network would look like. And the layer on the left that you see, which is that x1, x2, x3s, are the input layer. And in this case, that you have three different output that you are classifying the inputs into: y1, y2, y3. These are output class or output labels. The layers that you see in between are the stacked perceptrons. These are called the hidden layer. So the more hidden layer that you have, it's the more dense the neural network is. And there are some algorithms, some types of workloads require more deeply connected networks than the other ones. It's again based on the type of experiment that you are doing, and that will allow you to determine how many layers of these hidden layers that you would need. So we touched upon the activation function. There are multiple activation functions that are very much in play. The by default one is the step function, when the output of the summation activity that we talked about, and then how do you fire or not fire the outcome from that sum is what being determined by these activation functions. Step function is very basic, and it's of course it's not non-linear, so you would want to use something like sigmoid function, or the most famous ones nowadays are ReLU, and of course the TANH is also prevalently used. So there is another concept. When you have a deeply connected neural network, the important thing to note about is that how the gradient descent and backpropagation works, especially when you are training your inputs, and how you improve your model for each runtime, each epoch. How it works out is that you have this input, you have this densely connected network, and they are being trained and to determine the weights W1, W2, W3, W4 that, as we mentioned earlier, and that gets activated the next layer, and that goes as the input to the next layer, so go on and so forth. And finally, you have this activation functions. In the case of binary classifications, you can get away with the sigmoid, but when you have the multi-class, that you would want a softmax layer at the end, and that pretty much produces the output class that you are looking at. So when you calculate the first time, when you go through from left to right, and then you need to make sure that you have the right output, all you need to do is from the trained label data, you would want to check on what is the loss function between the desired expected output versus the actual output. And that's when there is a difference. When the loss is higher, then you would want to go back towards the right to left and readjust the weights, and that's what the process is called backpropagation. So it gets repeatedly done, and the gradient descent is the technique that allows you to find the local minimum for the loss functions that you would generate, and that converges faster than typical any other loss functions that you would use. And there are many ways to do it. There is a stochastic gradient descent, there is a batch gradient descent, and mini batch, and there are some advancements that are happening in this space to quickly converge faster, at the same time that the performances of the model is also higher. And this is the examples that you may have already seen from, this applies to linear regression or a logistic regression, so any of the classical machine learning that you would use, but it is heavily used in the context of deep learning. These are the frameworks that are available in the market today, and very famous TensorFlow is open source that is started from Google. There is a TensorFlow new version 2.0 is coming up. It's already there out there. And PyTorch is started by Facebook sometime back, and it's open source again. Now we have MXNet. Amazon chose MXNet as the default machine learning, deep learning platform framework. And there is a Chainer, Theano. And the next important one is the Keras. Keras is the higher level abstract API that can sit on top of any of the other frameworks that we see here. And Keras also becomes the default API for TensorFlow 2.0. So in the past that you would have to learn separately how the TensorFlow work, then the Keras on top of that. Now you can directly work with Keras, which is the default API for TensorFlow framework. Then there is the Microsoft Cognitive Toolkit, and there is one more called Gluon. Gluon is also a high-level API. In fact, both Microsoft and Amazon came together to develop the Gluon. So these are the different frameworks that are available. The most famous ones are TensorFlow and PyTorch, and of course the MXNet is also in play. And if you look at from all the big cloud providers, they provide the support for all of these frameworks, even though they have their own proprietary framework that they came up with, but all of them provide support in their cloud environment. And we're going to see some examples of how Microsoft provides this capability in Azure in a few minutes. Where do I apply for the deep learning? So we briefly touched upon how deep learning is pretty much used in AI, part of the AI ML. You could see the application of deep learning in image and video processing a lot. And the second major area where it is used is then the natural language processing. Lots and lots of language capabilities being used in the deep learning experiments. And of course on the audio data. So these are the top three, and you could use for any other purposes that you would use your classical machine learning, but at the same time, these are best suited for these kind of experiments. There are a couple types that I would want to talk about, which is like convolutional neural network. That's pretty much is what's used for your image and video processing, and the recurrent neural network is what being used for the natural language processing. And of course, there is another area called reinforcement learning. That is also it's also kind of a learning the model that based on rewards, pretty much used in the self-driving cars in that space. So quickly touch on convolutional neural network. We talked about it's primarily used for image processing, and it can be applied for many other purposes as well, but it suits really well for image processing. Here you have on the left side a handwritten letter or the number 2, and for the algorithm to figure out whether it is the number 2 or something else, then you would use that convolutional neural networks. It goes, the basic principle in this case is that it goes on the vertical cortex, the vision cortex that we use. So when you want to identify, recognize something, you may not need to look at the full image or the full structure of anything for you to be able to say what it is. And that's how our vision cortex work. The same or a similar logic is being used in the convolutional neural. You don't need to look at every single pixel, every single line in your image. So where you can take part of that and then you can build on top of that and then summarize that at the end is what the basic principle on how convolutional neural network work. The one other concept here in deep learning is called transfer learning. We all know that we do deep learning for large amount of data. You get support from your cloud. There are frameworks that are available. There are hardware that are available, but it still takes a lot of time. So the idea of transferring the knowledge that you learn from training one set of data and use that for a different set of data is pretty much common in this field of transfer learning. What I mean by that is that you have a data set 1 and data set 2. In the past, with the traditional machine learning, you would be learning from this data set 1, then you would use that model for prediction, which is similar for the data that you get from the data set 1, similar to data set 1. And then if you want to train something on data set 2, you create a separate model. But what you do in the transfer learning that is pretty much common in the deep learning space is that you transfer the knowledge of what you learned from the data set 1 to be able to use that for your training in the data set 2. So it reduces the learning time that it takes for training the data set 2. So there are some algorithms that are available called VGG16, 19, ResNet, inception, exception. There are many more. What you do is in this case is that when you have a convolutional neural network which is trained on ImageNet data set where millions and millions of pictures are being trained, and you learn the weights, the W1, W2, W3, of course with the biases, and you would detach the last few layers and you write your own new layers for the labels that you are trying to use from your data set 2, and then you retrain that. You would be training only the new layers that you added instead of training the entire layers that you trained your data set with. So that's how it makes things faster. Simple analogy is that if you're using a model that you learn from animals, and there are the edges and the shapes and the corners, and those things are common for even predicting different types of images, if not necessarily in animals. So those are the things that gets trained on the first few layers, but when you put together as a different object, and that happens towards the tail end of your network. So that's the idea behind this transfer learning. What do you do with deep learning in images? You can do classification. So basically you can tell what that object is, and you can not only classify but also localize that within that image. Like there is a cat and you can put a box around it where exactly that cat is in your image. And there is object detection. Basically, when you have multiple objects in your image, or it could be a video, continuous frames, where you can identify what objects are and where are they. And there is also something called segmentation, like semantic segmentation. So where you can exactly draw the boundaries of the objects that you are identifying. Those are the different techniques and different algorithms that are available for you to be able to use, for images. And there is another type called recurrent neural networks. These convolutional neural networks works beautifully when you have a fixed amount of inputs, when you know that what vectors that you would be creating from your data set, and those are like fixed size. But when it comes to sometimes like using natural language processing, where the input is not necessarily be of the same size. So in that case, there's something called recurrent neural networks come into play, where you would pretty much feed the output of the one layer that you would create back to it. In this case, the weights are being maintained same, and the number of times that you would repeatedly use this layer is practically like infinite. So you can keep on using that. So that's what is being used, especially for language translations and language models, and the chatbots, Q&As, and conversational Q&As, and things like those kind of use cases. You would use recurrent neural networks. There are many types of RNNs that are available. For example, there is a GRU and there is a LSTM, and now there is a bidirectional encoder architecture like BERT, and there are lots of advancements that's happening in this space. And now the output of any of these algorithms nowadays, it even beat the human capabilities when it comes to translations or even context-based conversational Q&A systems that pretty much everybody started using. If you go to a bank website, you will start seeing the chatbot, and that's pretty much be able to understand, work with you nowadays, and be able to answer all your questions and most efficiently. So that's the recurrent neural networks behind that. Yeah, so we talked about natural language processing. You can use the recurrent neural networks for named entity recognition, language modeling, sentence level classifications, when you want a semantic matching, and the machine translations and Q&A and image capturing. So you can provide an image, and the outcome from training and predicting exercise from that image could be what exactly is happening in that image. That's what's called the image captioning. So we have lots of capabilities, lots of new frameworks and opportunities in this space. So that gives you a very higher level overview of what deep learning is, what are the different frameworks that are available, and what you can do with that. With that, I want to introduce Azure machine learning capabilities from Microsoft. So we have that end-to-end workflow that you could use Azure machine learning cloud capabilities, especially which is in the preview now, to train, to package your model and verify, validate it, and deploy that into some sort of a REST-based microservices, and expose that for your further projections of any new data that you would want to predict or classify, and monitor, continuously monitor that for any active learning, for any new data set that you experience. And if your model is not performing to your expectations, then that goes as the input, and it's a feedback loop that you would want to use that new data to be able to train your algorithm again to improve the accuracy of your model. So the idea is to do that in a central place where you could have access to your data, where you have access to your storage, and then where you have access to your compute. You can spin off a CPU cluster or a GPU cluster or even an FPGA cluster, then train your model, train your algorithm onto the data set that you have, then be able to create a package out of it and then test it and deploy it and continuously monitor that. So we call that as the MLOps, similar to the DevOps that you may be hearing from the typical software world. Now for the machine learning, so you have the framework that's called MLOps. So to do that, what you need is the workspace. It's called the Azure ML workspace. What you get from the Azure ML workspace is that you have the compute instances that you would need, and you can create an experiment, and you can have access to the data sets. You can have a Azure storage that you typically get, and you will be able to run the model and store the snapshot of various stages, and you can also collect the metrics during your run. For example, that if you want to check on the parameters that you pass into your deep learning models, and you would want to check for multiple different parameters called tuning the hyperparameters. So you could do all of these things, and you can keep the history of what's being used, and also be able to detect which one is the better model or which parameters are better for your performance for your model. So you could do all of these things in one place, and it is like there is an RBAC role-based authentication that you can have, where multiple people can work together with the different privileges, and you have different compute targets that you can use. On the left side, you can see there is a SKU called Data Science Virtual Machine that comes with all different packages that are required, everything installed, pre-installed for you. And there is a machine learning compute, and you have a data lake, which is like You can store like very large amount of data which are primarily unstructured. And also you have the compute instances like Azure Databricks. Databricks is the another provider for distributed computing using like a framework or the API called Spark, and that allows you to distribute your workload and train them in parallel. And when it comes to deploying, you have options of deploying in a Kubernetes cluster where it is a containerized. You can put your web service, microservice that you would create out of your model, put it in your Docker container, and you can host it in your Kubernetes cluster, or you can choose Azure Container Instance as well. So that's the first-party container service that Microsoft provides. And you could, if you do not want to use Databricks, you could use HT Insight cluster. You can create HT Insight cluster for Hadoop or for Spark as well. And if you want to use some messaging, you could use it for Kafka queue as well to bring in your data if it is a streaming data for that matter. And also there's a lot more edge computing is the focus right now, where you do not need to send everything to your cloud to be able to predict, use your machine learning, deep learning models at the edge. So that's a support for edge is also provided in Azure ML Workspace. I also wanted to show you a cheat sheet. You can go to aka.ms ML cheat sheet. So it tells you like which model to use in what scenarios. All those things are very clearly documented. If you have time, that I would want to show a few minutes about how this Azure ML Workspace works in the Azure ML portal. So the code that I'm showing, the notebooks that I will be showing, it is hosted in GitHub. You can go to github.com/Azure and machine learning notebooks. And there are tons of tutorials that we put in there for everybody to use. And of course, you can contribute as well, as it is open source. So let me quickly switch to the notebooks. Let me know when you can see it. Yeah.
No problem.
Yes.
We see it.
Okay, great. So if you go to the GitHub, where you will see Azure Machine Learning Notebooks, so you see all the different options that are available for you. So some of the options that I would want to go through today is that you can train within a notebook. It's called it's called Azure Notebook. It's basically a Jupyter notebook that is hosted on Azure for you. Or you can train it on your local machine, right? You can, if you have a large enough machine that you would want to use it, you can do that, but I wouldn't recommend that for deep learning models. Or you can do it on train on a remote VM. So you procure a cluster or you procure a VM on cloud that you can train it on it. Then we also provide a compute cluster or ML compute cluster, or you can bring in your HT Insight Spark cluster. So there are multiple options that you can train your algorithms into. So I want to take you to using the Azure notebooks. And when you want to install your notebook, there are again 3 options that we give you, where you can use the Azure notebooks, which is the cloud hosted by Microsoft notebooks. There are some free options for the purpose of learning and doing some experimentation, or you can download and use your own notebook server. Of course, you would want to use the Anaconda. When you have Anaconda installed in your local, so you would use your Python virtual environment and load this certain Python packages called Azure ML SDK. Then you are good to go to do anything on your own notebook server. And we also provide option of containerized, like all these services that we are talking about. So it is available in the container form. If you are a fan of a container, which everybody is today nowadays, especially with the Docker and the Kubernetes that are available. So everybody wants to learn how to the good thing about container is that you can deploy it quickly and destroy it quickly and do your experiments and do a lot of and you can scale it also with the Kubernetes. So that's the beautiful thing about container. So we have that options as well. So I'm going to switch to using Azure Notebooks. So that is available for free for you to learn, and you can go to Azure and get that. It's called notebooks.azure.com. And of course, you would have to sign in with your Microsoft account. Then you have the sample tutorials that are available. So you have these things run on free compute, no charge to you, for you to be able to do these experiments. So we're going to use this configuration notebook to be able to set up the subscriptions and things like that to begin with. So this is the workspace, sorry, the notebook for that. So it is available for you there, where all you need to do is that you need to import in your Azure ML.core, and that would be already installed on your notebook. All you need to do is import. You don't need to do any other installation. The notebook is all completely come to you with all the setup backend required. So in that case, you just import it, and I'm not going to be able to run everything because of the limitation of the time. All I here masked my subscription ID for the privacy purposes. So all you need to give is the subscription ID there, and of course you would create a resource group, and if it is not already there, it would create based on what you provide here. So once you run that, then you are all set up. Now we would need to import that module called workspace from the ML package. Once you import that package, now you'll be able to either create a new workspace or be able to connect a workspace. If there is a workspace already there, then you would be able to connect to that workspace. So let me quickly jump and show you what a workspace look like. You can do all these things through the code, or you can go to Azure portal and then you can say, I want to go there and then go to AI machine learning, then say machine learning. Then you can create a your own workspace here as well. So it is, you can use the portal, but if you want more control, more power to you, like through using code, you can do that with this setup that we just talked about. And again, you can save this for any quick deployments that you would want to do later. So once you create the workspace, and that's pretty much comes with all the things that we talked about, from in terms of how you can ingest the data and what training algorithm to choose and what kind of clusters that you would want to use. So all those things are available, and you can create that your cluster using this code that you have in the cell. In this case, that it creates the CPU cluster with the skew that we have for D2 V2, and the minimum number of nodes is 0 and the maximum number of nodes is 4. So you can specify how many nodes that you would want in your cluster. So I did this for this demo this morning. So of course I created a CPU cluster, and that's much more most cost effective. Of course, you may not want to put your deep learning workload on the CPU cluster. You might need a GPU cluster for that matter. So you could do that GPU clusters in a similar the way you created your CPU clusters as well, right? So that's the idea behind this the tutorial notebooks that we have. So you can do all sorts of compute resources that you can deploy dynamically here. And there are FPGA clusters also available, and FPGA clusters are going to be very, very expensive. And if you really need to use FPGA, you might want to have a strong business case on why you want to use it. Then definitely that option is also available. Even if you need to use FPGA, I would ask you to train things at least in a GPU cluster with some toy sample data set before you even go into FPGA, because those are very expensive. So we provide this configuration notebook. So that's where you would set up. Once you set up your configuration notebook, there are many other tutorials that you can take advantage of that. So I would take a simple example here for how to train and deploy a model into a web service. In this case, that we are taking diabetes data set that we provide with the framework that we have. Here you need to import your workspace, the one that we set up in your configuration, and what we will be doing is creating an experiment for in this case. Again, I masked the subscription ID for I don't want to share my personal subscription ID here, but the idea is that you are leveraging the configurations that you created in the previous notebook, and you can check that everything is set up for us. So then again, I'm using a traditional machine learning notebook, and there is a deep learning notebook is also available, and it takes a little more time than the traditional notebook, but the steps are pretty much same. And I'll show you that at the end, like that notebook as well, so you can follow that if you are testing or experimenting a large amount of data set for a deep learning requirement. So you take your diabetes data set is the sample that we are using here. So we are using the rich linear regression, and you train by creating a new experiment on the workspace that you created, and you use the notebook that you would want to use for your training. During the process, you keep logging what's happening, your training progress, and at the same time that you're picking your algorithm that you would want to train, and you fit the model, and you would want to use your prediction based on the model it trained. So it gives you the mean square error in this case as the loss, and this is the notebook or the cell that trains your model. And once you train it, you could go back and see the results here, whatever you print here, or you could go to your Azure Machine Learning Studio portal, and it will show you what's going on for the model that you just trained, right? So you can go and see, look at it. It tells you the workspace that you are working on, the experiment that you're working on, the notebook that you're working on, and the run number 22. So, and gives you all the metrics that it collected. So it keeps track of all the things as part of the workspace that you have in the Machine Learning Studio. You could do all these things with the GUI as well, but I think it's more power for you to do that in the notebook. So obviously that any machine learning models, your parameter sweep is the grid search that you would do in terms of making sure that you have the right parameters for the accuracy of your model. So you could do that, all the parameter sweep, and then you can look at all the different experiment results. Again, you can go back to your Machine Learning Studio and then see all the results that are available to you, and it is permanent for you. You can keep looking at it and then keep changing whatever you would want to change to make it better. And the process, after you run all the parameters, then you would want to select the best model that you would want to use, right? So it gives you what is the best learning rate and the mean square error. And once you're comfortable that you are choosing the best model, that's when you would want to come to deploying. For deploying, you would register the model based on the model that we selected as the best model, and give the path from the previous step on where that model exists. And once you have that, then it basically registers that model. Then you create your environment based on the registered model, and you would use the custom score.py that is also available in the GitHub. And then you would want to figure out on what kind of deployment target architecture that you would want. Do you want to use the Azure Container Service, which is the first party service provider for the target container, or you would want to use the Azure Kubernetes service? Kubernetes is the open source, and it is offered through Azure as well, and that's very powerful as well. So you could choose whatever the target compute environment that you would want, and you can use that. Once you pick that one, and you can set the configuration of like what kind of target environment that you would want, then the next step is to deploy as part of as a web service. So you would create a web service, a REST endpoint for the model that you trained and picked the one as the best and registered with your Kubernetes service or Azure Container Service. Once you deploy it, and you want to test, and when you run it, then you get the output as like all you're doing is that you're going to the web service endpoint, and you could call this endpoint wherever, from your mobile app or from your code or from your website or wherever it is that you could call and make sure that it works perfect. And then you could draw your residual graphs and all sorts of analysis that you would do. The same thing, you could do that for the deep learning exercises as well. And when you go back and see, and this is the workspace that we've been looking at, so you have all the notebooks, the data sets, the experiments that you create, and if you want to, the steps that we went through, if you want to do that repeatedly in an automated fashion, so you create the pipeline, the deployment pipeline, the continuous integration, continuous deployment, and you could do that and automate it, like you can make it run every night or every other day, whatever the frequency that you would want, and you have access to all the models that you create and the endpoints, which is the REST endpoint that you would want to use, expose it. The one other thing is that it is secured, so it comes with the integration with the Azure Key Vault service. If you want to encrypt your keys, and there are a couple of options, like there's a Microsoft managed key service or a customer managed key service, so you could use any of these options to protect your endpoint and only allow access to the people that you would want.
We are Starweaver, education you can bank on. For more information, contact us.